Golovin couldn't come, so my name is Dmitry, so I will present this talk. And the title, I struggle with this stuff. Okay, now can you hear me? Okay, it's fine. Now, and the title of this talk is it just reflects the objectives of our work. So what we are trying to do in this work, we are using the ability of the land instrument to analyze the changes in the cosmic ray fluxes during the flight of LRO. And since we are going through the very interesting time, now we have a historic low solar minimum, so we will provide some analysis. And in this analysis we will use also the data from some other instruments. So now, this morning it was a talk presented by Bill Boynton, and in this talk he gave a very good description about the land detector. So this is our this is our detector hidden in this low right corner, and it's the heaviest detector on board of LRO, 22 kilograms, and most of it comes to the collimator. So the collimator, which is filled with boron. We have a number of sensors at land, and they measure not only neutrons but charged particles as well. And as to neutrons, they can measure neutrons in the different energy ranges, from thermal to epithermal and to very fast. Okay, so this is the schematic of land. So we have epithermal neutrons, epithermal sensors. They are collimated, and this is uncollimated. And we have thermal neutron sensor and high energy neutron sensor, and also charged particles. So a number of those. If it comes to charged particles, it's straightforward. Charged particles are related to the cosmic rays. But neutrons are a kind of derivative of cosmic rays. So what's going on? Cosmic rays are bombarding the surface, lunar surface, and the spallation produces neutrons. We have a flux of neutrons, and this flux of neutrons is detected by the land. And the intensity, the flux, it's just depends on the cosmic rays, on the cosmic rays intensity. Okay, now this is a number of instruments which we are using in our analysis. First, and this is our main instrument, is a land which is flying around the moon. It gives us neutrons in different energy spectrum. It gives us charged particles. Now this is the Earth, and we're looking at the neutrons measured at the surface of Earth. In fact, we're looking at McMurdo station, this data. This is a Mars, and on the board of Mars Explorer, it is a neutron detector, which is quite similar to whatever we have on the land. Besides, it doesn't have a collimator. So we also will analyze this data. And finally is AC. AC is in the liberation point, and it measures protons with energy 100 MeV and up. So now, this is what we're doing. I start with neutron fluxes. This is what can be done with, this is we're done with thermal neutrons. This map just shows the results of observations with the thermal neutrons, and this is a lunar surface. And this is how it goes with the flux of thermal neutrons. So it goes up, it peaks somewhere about January of 2010, and then it drops by about 15%, and then just fluctuates. Similar picture we have with the epithermal neutrons. And epithermal is in the energy range from 1 eV up to 1 MeV. And still, this is a picture, this is a map of the lunar surface with the help of the epithermal neutrons. Similar behavior, goes up, peaks at about January, and just drops of 2010 and then drops. Now we put it on the top of each other, and plus we put AC data. It's protons, I know, but it's this, they behave the same way. Now we look on the charged particles now. This is AC, this is LAND charged particle detector. So when this was low solar activity and with no solar events, definitely they behave similarly. I mean AC and LAND. In this case, a strong difference, but it was a solar event at the time. And LAND, I believe that LAND and AC, they have, we don't have, of course, this cross calibration, but they have different sensitivity to the low energy protons. Now, more experiments, more trend. Now, in this case, we put on the top of each other LAND, black, HAND, Mars Odyssey data, also neutron data, and McMurdo neutron data, and AC data. So you see, LAND and Martian data, they are quite close. No, not Martian. LAND and AC data, they are quite close. When it comes to Martian and to the data by McMurdo station, of course they peak at somewhere at 09, but then they drops much faster. So in a sense, what this peak is much more extended. Peak detected by LAND and by AC. Some theoretical estimates, but I need to mention that much more detailed analysis will be presented this Thursday in the talk by Sagdev. We start with the flux of galactic cosmic rays, which is a phenomenological equation given by Reedy. Its energy. What is the most important and marked by the red is the solar modulation potential, which is due to the effect of solar magnetic field on the galactic cosmic rays fluxes. I have to mention that it's given in the units of MeVs, in energy units. It's called potential, but is presented in energy units. This is alive. Okay, and this is potential. It ranges from 100 MeV up to more than 1,000. 100 MeV, it was in local interstellar medium, and more than 1,000 in period of solar grand maximum. But during the last historically low solar activity, it is estimated as about 250 MeVs. Now, some examples. What we see now is the proton spectrum computed for different solar modulation potentials from the top to bottom, 100, 200, 300, and 550. So it's a very significant variations depending on the solar modulation potential of about the order of magnitude. And next step, what we do now, this is the charged particles. Now we come to neutrons. So in the case of neutrons, we use the neutron production rate. So we compute neutron production rate by a charged particles using results by McKinney, who did a very meticulous, very good work computing the production rate when a single a single proton hits the ground and produces neutrons. So now this is a production rate by McKinney. This is the flux, which comes from the previous slides. And the result of computation is this. So this is solar modulation potential. This is neutron production rate. Now, this mark shows the neutron production rate is just normalized by its peak. It was at 250 at the peak, F250, and this is what it comes here, like a year after that, after the peak. The drop is about 15%, which is consistent with our observations. Now I come to the conclusions. So land has multiple detectors, as I mentioned, charged particles, neutrons, and all profiles of neutrons and particles are shown same shape with peak at January 10 with following decay until mid of April 2010. And it correlates well with temporal behavior of high energy protons measured by AC. But we have a mystery. No foggiest idea so far. The data collected at Mars and Earth, planets which have an atmosphere, have the peak extended by 2 months inside the stronger solar activity, unlike what we have at the Moon and by AC. Thank you. Okay, thank you.